2 hours of time with me. Who's excited? You can hold the applause till after. Okay, so we're gonna go right in to naming, which is everybody's favorite. All right, so right here, I made a little chart, which I stole actually, so I didn't really make it, which actually just breaks down the base name and the common names, IUPAC names, things like that. So for alkanoic acid, so here's an example. It's not really, it was supposed to be a different color, but I can't afford colored printing. So that's just how it is. So for, if I was naming carboxylic acid, I get rid of, or I change the E to oic acid. Does that make sense? Okay. And then that's the IUPAC name. And then we'll go to the common name. Just a heads up, if you can't see the rest of the paper, just like holler at me and be like, yo, move it or something. Okay, so this is just one example of ethanoic acid, acetic acid, common name, IUPAC name. So let's go for the acid halide. All right, for the acid halide, you take the IC and you change that to YL halide. And it's also very similar with the other one. So the IC acid, you take that off and change it to ill halide. Is everyone good with that? So for this one, we go for the parent chain, which is 2 carbons long, right? So that's a suffix of eth, ETH. So this is going to be ethanol chloride. Is that cool? And then for the common name, we just went over it, so acetyl chloride. So this naming, I think, is chapter 21, all the derivatives. So this is just a review of that. If you can't read anything, by the way, I'll write it nicer. And if you have any questions, like raise your hand. We'll go through. We actually have a lot of time too. Okay, so for the next one, anhydrides are actually pretty easy. You just get rid of acid, and then you just add anhydride. And it's the exact same for the common name. Get rid of that and add anhydride. Is that cool? So in this case, you would do the same thing. So carbon parent chain is 2 carbons long. So it's ethanoic anhydride. Okay, and then same for the, oh, did I say common name? IUPAC name. So common name in this case would be acetic anhydride. Wait, did I? Yeah, okay. Okay, so for the ester, we have alkanoic acid and alkanic acid. This one's also, you change the IC acid part, you get rid of that, and you add O8. Forgive me if I'm going a little fast for naming. It's just like somewhat of a review. So after, wait, sorry, you add 8, that's it, my bad. This O stays, so you just add ATE. Is that cool? And then same with the alkanic acid, you add 8. All right, so in this case, you would first name this one, the one attached to the O, so it'd be methyl ethanoate. I guess a weird way to remember esters or noate, you can be like Esther no8, like she didn't eat type thing. Kind of dumb, but it'll help you remember it later. Okay, so for the next one, it's going to be methyl, same thing, you name this part first, methyl acetate. Oh wow, okay. All right. So all good with this one so far? Everyone's good with naming? Yeah, you can just find these in the chapter. I just felt it would be easier to just make a chart, just easier to access. Okay, so let's go over the next one. Amides are also pretty decent. you get rid of oic acid, and you just add amide. And same thing with this one, get rid of IC acid, and you add amide. Is that cool? Sweet. So for this one, 2 carbons long, so it's going to have suffix of ethyl, so ethanamide. And then my common name is going to be acetamide. Okay, so for my nitrile, we're going to get rid of oic acid and add O-nitrile. And then same thing with my common name, get rid of ic acid and add O-nitrile. Okay, so this one's going to be 2 carbons long, ethanonitrile. Cool. Oh, did I? Is it all good? Let me get rid of that. This will also be on YouTube and like live stream right now. I mean, you don't have to see the live stream because you're here, but 24 hours after, it's going to be on YouTube at some point. So if you didn't get something, feel free to check there also. Okay, so and then same thing with a common name, acetonitrile. Is everyone good with this naming thing? So after each question, I'm just going to ask, like, do you guys have any questions? Everyone's cool with this? Okay. So let's head on to the next page, which is you guessed it, more naming. Okay. So this is easy enough. You guys recognize this stuff. On the ACS, I blanked out on the triple bond one, alkynes, and I was like, I have no idea what it ends with. So I was surprised every time I saw we'll start with that one, a YNE. Okay, so this one is going to be ENE, alcohol is going to be OL, this one will be just an amine, aldehydes are AL, and then ketones are O and E. Okay, so a little thing with ketones and aldehydes, if you have a ketone and aldehyde, say on the same ring, or same compound, so example, let's say if I have this structure, usually what you'll see is that they'll name the ketone group as oxo, and your aldehyde will have priority, so you'll still end with AL. So like 1, 2, 3, 4, so like butanal, and then 1, 2, 3, 3 oxo butanal, something like that. So if you see oxo, that means the ketone's not taking priority, and usually aldehyde will, and that's just trying to tell you that there's a ketone there. Okay, so ethers have a little weird. They have 2 ways of naming it, so let's do an example right here. Let's do a methyl ethyl ether. Okay, so one way of naming it is to say alkane, alkane, ether. So in this case, we would go by what? How would we order methyl, ethyl? Which one would go first? Good, good guys. So yeah, you go by alphabetical order. All right, so this in this case would be ethyl. Actually, I'm gonna put alkane, alkane, ether. Or specifically alkyl, so ethyl. So change the A into YL, my bad. So this one would be ethyl, methyl, ether. So that's one way of naming it. The second way of naming it is to name it an alkoxy alkane. So I'm just going to put divider right here. Alkoxy alkane. And to choose which substituent is going to be the alkoxy group, back to I'm going to draw my example here again. I would choose the shortest substituent to be my alkoxy group. Is that cool? So for this case, this would be methoxy. Methoxy ethane. Does that make sense with everyone? So there are two.
How does that go again? I'm sorry, the methoxy. How do you get the
Okay, so
instead of methyl ethyl
this one?
ether? Yeah. How do you get the second one? It's just
So yeah, for the alkoxy group, it's going to be the substituent that's the smallest. So you add oxy to whatever the smallest substituent is. So in this case, it's methyl. So you just change it to
if it was
methoxy.
two ethyls, would it be methoxy ethane?
If it was two ethyls, that one, it may be easier to just name it with this one. I think that's where the two A's come in. Yeah, I think ethyl or diethyl ether would probably be its normal one. Yeah, they probably want to name that with using two ethyl groups, just like a little weirder. I don't think they want to do that. Okay, so this is a loose guideline. That's a good question though, by the way. So this is a loose guideline for naming. So for identifying the parent chain, what you want to do is identify which functional group has priority. And the way to find that, there's like a chart, like just look up IUPAC functional group priority, and it'll give you a chart of what takes priority, and that'll give you your ending part. Usually alcohols take priority most of the time, you know? So the first thing, I guess, would be to write priority, FG. So find that, which is FG's functional group. Okay, so and then the next thing is identify names and substituent with the lowest number locants. Does that make sense? So if like I had to name on a ring or anything else, I would want it to be like 1, 2 versus like 1, 5, 6, you know? You want your lowest numbers. Does that make sense, everyone? Okay, so our next one is arrange substituents alphabetically. So when we're naming alphabetically, just make sure you don't include di and tri, because those don't count under the alphabetical thing. Is that cool? So all the suffixes, di, tri, whatever, they don't count. But the one exception for that would be iso. Exception is going to be iso. So like isopropyl, iso something, you're going to count the I as like part of the alphabet. Does that make sense? Yes, no, maybe? You look really confused. So does that kind of make sense for you? Okay. So that's going to be iso. So that one will actually count the I. And then lastly, we will indicate any stereochemistry. So for this one, what is the proper name for this compound? Let's just go by and see what we can. So like an easy way to approach the ACS, just start eliminating as much as you can. So the one that sticks out to me is C. Why is C the first one that I want to eliminate? Does anyone have a clue about that? Even though it is meta to this and ortho. Good, yeah, so we can only use ortho and meta when there's only 2 substituents. When there's 3 substituents, you can't use meta, ortho, para. Is that cool? So immediately C, we throw that out there. Okay? So back to our step 1 priority functional group. In this case, it's gonna, no one told me to move it up. You guys are looking at nothing? I trusted you guys. Okay, so back to this one, so we can actually see it. Okay, so the alcohol is gonna take priority in this case, right? So we can also remove A. So there's like a list online, kind of as I mentioned. And then which way would I go? Would I go 1, 2, 3, or would I go 1, 2? Which do you think? Good. Nice, Angie. So yeah, nitro would be my 1, 2, and this would be my 5. Just the numbers are easier. So if I look for a 2, 5, that would be D. Cool. All right, so what is the is everyone good with that question? All good? Okay.
OH just gets priority over the others?
There's a list of, it's not like for like a specific, it's not like atomic number or anything. It's just like a list online. IUPAC people decided that. I don't know who they are. I don't know why they do that. They're weird sometimes, but like, yeah, that's them. Okay, so what is the IUPAC name for this compound? Once again, let's just kind of like attack it and see what we can get rid of. So just by looking at this one, I see my amide here, and when I'm naming a substituent off an amide, I usually put N, right? So the one that doesn't have N is this one. So that's out of there. And this also doesn't have an N, so that doesn't make any sense. So now we're stuck between chlorophenol and chlorobenzyl. All right? So between our the difference between phenol and benzyl, once again, this is the IUPAC people, it's like not me making this stuff up. So a phenol group will not have a carbon off the ring. So if I had like this, that would be my phenol. But benzyl would be, does that make sense? That's benzyl. Mm-hmm. Good. Yeah. So yeah, phenol will not have a CH2. That like squiggly line's like a cutoff point. Is that cool? So this is not a carbon. That thing. Okay. Is everyone good with that question? Oh wait. So the answer would be, in this case, phenol. Is that cool? Okay. So the next question, number 3. Name the following compound. So once again, it was A. So name the following compound. So in this case, I'm going to start numbering it. So 1, 2, 3, 4, 5, 6, 7. Okay? And then the 3 functional group kind of things I'm going to look at are my OH, substituent of methyl, and my alkene will also be a substituent. Okay, so let's go by, so we identify the parent chain, so that's going to be hept as 7, and it's going to end with OL. Okay, and then we have a 5-methyl and a 4-hept, like a double bond. So let's start with that part, because I think that's easier. So hept, 5-methyl, 4-hept, EN2, OL. So that's that part. Does that make sense? I think a way to go back on naming is like, if it was asking me to name the structure, what I usually do is like, I'll cover up that structure and be like, can I name it off what I just wrote? And if I can't, then I probably did something wrong. Does that make sense? It's just like a way to like check yourself. Okay, so the last thing we need to do is indicate any stereochemistry. So for this case, we'll have a few more stereochemistry problems later. So this one I'm probably just gonna like slide through. Okay, so oxygen is gonna be priority 1. This methyl group with 2, this will be 3. So that's gonna be R. So we have a 2R somewhere. And then for this one, for the double bond, we have to indicate E or Z. And both of the large substituents are on different sides, so that's going to be E. So it's going to be 4E. The way I remember it really probably won't sit for anyone else. I remember same Z, like Z as in like they're on the same side, like same Z. If that doesn't work for you, it also confuses me though, so maybe not use that one, whatever works. Okay, so then we just add that in parentheses at the front. Anyone have any questions on this one? Yeah, so I look at this alkene right here, and I would look at this carbon, and I'd look at this other carbon that I circled, and then I see which side has the biggest substituent. So like this one has a substituent, and this one has the biggest one, and they're on opposite sides of the double bond. If in this case, they were like, they're on the same side. This is the worst alkene I've ever drawn. So if they're on the same side, the large substituents, this would be Z. Does that make sense? What's up? Mm. Over the alkyne. That I can't say for sure, just because I don't remember that exception. Um, but yeah, tell me, I'll look it up after the session. But yeah, I honestly don't remember. But yeah, that's a good question. All right, so the next one, is everyone good with this one? We're all cool? Okay, cool. All right, so the next stuff, let's get rid of that. A little review on functional groups. If you see this question on the ACS, you should be like ecstatic, because this is like a great giveaway question. All right, so let's just go through it right now. So we're looking for an amide, a ketone, an ester, and an ether. Okay, so for this one, I see a ketone. For this one, I see an ester. I guess I'll quickly draw these up top. So this is an amide. This is a ketone. This is an ester, R group, and this is an ether. So I'm looking for all of these in one compound. Okay, so this one just has a ketone, ester, and, ether, and an amine. So it does not have all of them. So it's not that one. So this one's a ketone, ester, ether, amide. So I'm guessing it's B. Cool stuff. All right, is everyone good with this question? We're all good with functional groups? It might help to review anisole and aniline, because I know that was a favorite for one of the tests. Okay, so the next part is structure, hybridization, resonance, and aromaticity. All right, so constitutional isomers have the same molecular formula, but different connectivity of atoms and identical or different physical properties. What do you guys think? You think that have identical or different? Good, but in this case, it's actually different. Yeah, so they should have different physical properties. I just think of it like they're called different things. So they're different. So this one will be different. So hybridization is determined by the number of sigma bonds and the number of lone pairs. So nothing else matters. So an atom that has sp3 hybridized has orgo1 and GenChem stuff, which is once again everybody's favorite and a throwback. So this one's going to be tetrahedral. The sp2 will be planar, and this one will be linear. All right, so aromatic compounds contain a planar ring with conjugation, or is it fully conjugated ring? And then that Huckel's p orbitals and Huckel's number, which is 4n plus 2. I think the first thing I did when I got 4n plus 2 was solve for n, which is the wrong thing to do. You don't have to solve for n. N can be any integer, and you're just seeing if it can equal how many pi electrons you have. Is that cool? You with that? Okay, so the next one is draw Newman projections that represents the most stable conformation of that thing. So what I like to do, I don't really know how to read this, so I like to draw it in like the line bond format. So get faster at that, like practice. I think you got a ton of it on your test that like tripped people up, but it's all over the ACS and it's really easy to get stuck on it. So I think the first thing I'm going to do is draw this structure. Okay, so that's my structure. I have the two CH3s, the CH, CH, CH3, CH2. Okay, so now I'm going to add my wedges and dashes to it. My wedge. Make this one a wedge. And then this one should be a CH3. And same thing. Wedge, dash. Okay? So when I'm drawing my Newman structure, which I don't think anyone likes Newman structures. That's nice to hear. It does make sense once you get it. Okay, so when I draw this first like triangle structure, that's representing the carbon that I'm looking at. So if I was like I don't have the bond line structure, but if I was looking at it, if I was flat on the page and I was looking at my carbon from this point, this carbon right here is going to be this carbon right there. Okay? Is that cool? So I'm going to draw my circle. That's not a good circle. I'm going to have line here, line here, line here. So all the lines on the circle represent your second carbon, the one right behind the first one. Okay? So this circle, all these three lines represent the three connectivity things of the second one. I'm not shaking because I'm nervous, I'm shaking because of coffee. There's a difference. All right, so the next thing we're gonna look at is what's in plane with my page, basically. So the ones that I drew with a line, the CH3 and the CH3, if I had my paper like this, they're like flat with the page, right? Does that make sense? So like they're not sticking out of the page at all. So that would be the ones that are not on wedges and dashes. And conveniently, they just go up and down. So on this one would be this CH3 right here. And then this one would be this CH3 at the top. So this is like, I'm tilting my molecule and I'm looking at it on top of it. Is that cool? So we have a wedge coming out at us right here, out of the page, so it's gonna be on the right side. Does that make sense? Okay, so that's gonna be over here. And then we have a dash going into the page, so it's gonna be on the other side of this paper, so it's gonna be on the left. I was not sure how to show that physically, so I just pointed the paper. So that's gonna be an H. Is that cool? So same thing for this one. I have a CH3 coming out of the right side, or coming out at us, and I have a wedge hydrogen going out into the inside. Okay? So it's asking for our most stable conformation. Does this look stable at all to you? No, right? So there's too many gauche, gosh, I don't know the pronunciation, interactions. So we're gonna have to like take this triangle part and just twist it a little bit to get an easier interaction. Okay? So I'm gonna move this one clockwise. Good, thank you. Clockwise. So I'm gonna take this one and move it clockwise so my CH3, this one goes here, this hydrogen goes this way. So they're all just gonna switch spots. So I'm gonna draw the same thing. I have my CH3 still there. Let me draw the circle first. The ones on the back are gonna stay the same. And then this CH3 is gonna be here. This CH3 is gonna be there. And then this hydrogen is gonna be there. So now if you look at it, these CH3s right here are now anti to each other. We're all cool with that. And then same with these hydrogens are also anti to each other, which actually is really nice now because now these CH3s aren't chill on the same spot. So now these are anti, they're all anti to each other. Makes things a little easier. You don't have those gauche, gosh interactions. So I'll go with Newman stuff. Okay.
Did you just choose like the wedges and the dashes like arbitrarily?
I kind of oriented it to fit my Newman structure easier. So in this case, the two lines up here going straight up, I made it so the two are going up here. Does that make sense? And in this case, I made them go down because I know my Newman structure lines go down here. So just easier for me to draw. That's a really good question. So yeah, that just really helps my Newman structure. So I just make sure the first carbon stuff goes up the wedges and dashes, and in the second carbon, I just make sure they just go down, just so it fits my Newman structure. Good question.
Wedges go on the right points and dashes go on the left points.
Yes. It's more like the wedges, if once again, if my page was flat like this, the wedges are coming out at us, and now I'm twisting my molecule to come out like at you. So now my wedges. Does that make sense? So like my Newman structure, the wedge would be like this. So it's going to be on that side. If this was like this is hard to do with a paper and a pen, explanation wise. All right, so we're all good with this one?
But if you looked at it from the other carbon, wouldn't the wedge be on your left?
Would the wedge be on my left?
If you looked at it from the other carbon that we did.
The second one? It's not that it's on my left, it's that it's coming out of the page. So if it's coming out, they're both coming out at me, they're both going to still be on the right side. So if I had this carbon, if I had two of them, this is a bad explanation. So this is one carbon and this is another carbon. So they're both still coming out of the page. So it's going to be on your right side still when I turn it. Does that make sense? Okay. I wish I brought the line, that structure thing you guys get sometimes. Okay, so we're good with Newman structure a little bit? All right, cool. So we're going to move on to the, yes. So do it from the first carbon? Yeah, let me pull it up, 1 second. No, it's okay. This one's it. This one. Oh, for the Newman structure? Would be on the circle, you said? Mm-hmm.
I don't think that matters. Like, you don't have to draw the line down. You can draw it up.
Oh, for the Newman structure?
Yeah, it doesn't matter where they.
Yeah, because it rotates anyways. It just, that's where I start. But it, yeah, like you said, it rotates. Just make sure the one on the triangle is the first carbon that you're looking at. Does that make sense? But yeah, like you said, that was good. It rotates, so it doesn't have to be like starting like that. Is that cool? Thank you, by the way. That was good. Good answer. Okay, so we're good with this. All right, so we're gonna move on to the next stuff, which is, did I take it away? What page is next? Oh, okay, cool. Sweet, thank you. All right. This is fun stuff. Okay, so first we have to check what, which is kind of hard for me to ask you that since you've only got this review like today, so you guys haven't really got to look at it. So in this case, the first thing we're going to check is if everything satisfies my octet rule, because if it doesn't, then it's not gonna be comfortable. So let's look at my first one. Does my nitrogen satisfy the octet rule? And I just do that by counting the electrons around it. So in this case, it's got 2, 4, and 6, 8. So I just count both electrons in each case. So this nitrogen satisfies the octet rule. Let's look at the next one, 2, 4, 6. That does not. So right away I can eliminate A. So those second period elements, so second column elements, they should not be messing with the octet rule. So by second column I mean carbon, nitrogen, oxygen, fluorine, all of those. They are sticking to that rule. They really don't want to mess with that. So that one's gone. Let's do this one. So does this satisfy 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6. Okay, so this one satisfies the octet rule. So I'm just going to go through really quick and see if they all satisfy the octet rule. Okay? So C is good with the octet rule. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, okay. 2, 4, 6, 8, and 2, 4, 6, 8. All right, looks like they all satisfy the octet rule, unless I missed something. So now let's look at charges. So nitrogen has 5 valence electrons. Oxygen is 6. and I think those are the only two we're discussing in this question. So in this case, nitrogen only has 4 electrons bonded to it, or in its valence shell. So this is going to be +1, so it's just a positive. This one's neutral, and this oxygen is 7 electrons, so it's going to be negative. So now let's look at this one, 2, 4, 6, 7, so that's -2. That's way too many. That's -2. This one is 1, 2, 3, 4, so +1, or just plus 2, 1, 2, 3, 5. This one has, does anyone know how to add? I just blanked out on adding. Thank goodness you guys are here. And what about this one? Nitrogen would have minus, good. Minus, this nitrogen plus, and this oxygen is good. Okay, so we know A is out of the question because we just discussed that. This one has a bunch of charges on it, which is terrible. So it's probably not going to be D, just because the less charge you have on your structure, the better. You don't want multiple charges. Okay, so I'm going to take off D. So now it's between C and D, C and B and C. In the end, plus and minus are neutral, so we can't go cut it down by that. So what we're going to check is where the charges are at. So in this case, we have an oxygen with a negative charge and a nitrogen with a negative charge. Which one do you think is better at holding that negative? Nitrogen or oxygen? That's a good. It's actually oxygen. Actually, oxygen is better at holding that charge, especially since it's larger too. So if you go electronegativity on the periodic table, the trend is like, it's like, I'm not drawing the periodic table. Let's just do FON, most electronegative atoms going this way. So fluorine and oxygen are better than nitrogen, if that makes sense. Periodic table goes the other way. I just remember it as FON. That's how I remember it. But yeah, your trend should be going a different way. So oxygen is actually the better one at holding the charge. So it's going to be C in this case. Is everyone cool with that? Okay, so now let's look at 7, which is which of the following structures have 8 pi electrons? So this is aromaticity. I think this is chapter 19 or something. All right, so let's count my pi electrons. So what do you guys think about 1? Does it have 8 pi electrons? Cool. So it's got a lone pair here, got a lone pair here. Both these lone pairs can participate in resonance with the ring at the same time, so definitely have 8. Cool. Okay, so let's look at the second one. Oxygen has 2 lone pairs, but can they both be participating in resonance at the same time? No, right? It only one would. So this one has 6. I think a way to like look at it is if I tried to draw this, oxygen would then have like this double bond structure, and that's somewhat linear, and that would break the ring, and now it's looking weird. You know, it's positive. That's just not good overall. I think that's sp2. So yeah, don't do this one. What about this one? 3. 6, right? The way I remembered it, like trick-wise, was anytime there's a double bond attached to something with a lone pair directly, that lone pair cannot participate in the ring even if it wanted to. So if my double bond is attached to something with that lone pair is not participating in aromaticity. Reasoning is just that it's in an sp2 orbital, not a p orbital, if you actually wanted the reason for that. It's just in a different plane. It's not going to be part of it. So we're all good with 7? Okay, cool. Oh wait, I just take one. Never mind. I'm moving too fast. All right, let's go to 8. All right, so which of these structures is or are aromatic? What do you guys think? Just a brief, what do you guys think about 1? Is that aromatic? Fully conjugated? And it fulfills Huckel's rule is, yeah. Cool. All right, so 1's good. So then we can eliminate this one. What do you guys think about 2? 2, 4, 6. Good, aromatic. This is sp2, so it has an empty p orbital. So that's definitely aromatic. So the two rules are, I think we went over this before, fully conjugated, and second rule, 4n plus 2. So if it's not fully conjugated and it satisfies Huckel's rule, then it's non-aromatic. I don't think you guys did a different thing for that. I learned it to be non-aromatic. I think you guys learned it differently, so we're not going to talk about that.
It's anti-aromatic if it doesn't.
If it fulfills Huckel's rule?
If it's conjugated but doesn't equal that,
Yeah, that would be.
anti.
But if it's not fully conjugated,
Then it's
but
just not.
fulfills. You guys say not?
Non.
Not. Okay. Okay. I guess we learned it the same then. I don't know if it's going to be on the ACS. I think they'll ask like questions more similar, like which of these are aromatic. I don't remember a specific question on the ACS where it was like that, but that was my ACS, so I'm not too sure. Okay, so we're still on this question, right? Okay, so what about 3? Is that aromatic is that aromatic? Yeah. Good, does that make sense to everyone? 4n plus 2, if n was 0, I would equal 2. Yes. I'm not good at math, that's why I'm here. Okay, so 3 is aromatic. What about 4? What are you asking about 4? No, why do you say no? Good, nice. So boron does not have a pure orbital. In general, boron's in your ring, it's probably not going to be aromatic. Just like throwing that out there, just like a thing that, because boron in general only has 3 valence electrons, it doesn't have that pure orbital, and usually just boron's a little weird. So we're going to go with D. Okay, so in which of these Lewis structures would sulfur be assigned a formal charge of positive 2? So how many valence electrons does sulfur have, and how do I know? 6, right? Good. So it's in the same column as oxygen. So like a brief knowledge, or not brief knowledge, somewhat memorize a few elements on the periodic table would be boron, carbon, nitrogen, oxygen, fluorine. And then they should.
There's a formula sheet and there's a periodic.
Yeah, they should. Yeah, that's good. Thank you. But yeah, maybe just know these in order, because like valence-wise, 3, 4, 5, 6, 7, and these are all 6. So it's just like a quick way. But yeah, periodic table is provided. You don't have to memorize this. Okay, so now we're looking for something that only has 4. Thank you. Thank goodness you're out. Math is not. All right, so let's look at this one. So 2, 3, 5, 6. So we're good with this one. Sulfur is neutral in this case. Everyone agree? Okay, so this one's good. What about this one? What charge does it have? +1, right? 2, 3, 4, 5. This one has so +2. Is that cool? I don't know, I'm acting surprised like I did this test. This is not a surprise to me. +2. Okay, and then this one, 6, we're good. So we're good with assigning formal charges. We're looking at valence. Nice. We're only on question 10. Oh my goodness. All right, cool stuff. All right, for which carbocation can the most resonance forms be written to show the delocalization of the positive charge? So just looking at it, which one doesn't have resonance? B, right? So B does not have resonance. Are what's it called? Vinyl carbocations, do they participate in resonance? Are they stable at all? No, right? So these are not that stable. So D is definitely out. So even if I like tried resonance, that carbocation is just not a thing that's going to move around. It's not really going to do much. Between C and A, which one has more resonance? Good, yes. You guys are geniuses. C. Oh, you got to believe in yourself. Okay, so in this case, it says more resonant. I'm not going to draw the resonance structures if you want me to. Yeah, I'm not. I'm sorry. It's just not. This is actually just not going to happen. Okay, so next question. We're going to look at the carbene. This is weird. ACS will throw stuff at you that you will not recognize, like this. Just don't worry though, because you've learned the concept, right? So you can like break it down, even though you've not seen this carbene thing. Honestly, looking at it, if this wasn't there, I'd be like, oh, a carbon with a double bond, and then I'd get that wrong. But thank goodness the structure's here. So what is my hybridization? The only thing that matters, kind of like we previously stated, was my sigma bonds and lone pairs, right? So in this case, I have one lone pair and two sigma bonds. So the quickest way to do hybridization is just to count what it's connected to. So 1, 2, 3, so minus 1 sp2. Is that cool with everyone? Discounted? Yeah. So let's do a simpler one, CH. So in this case, I just find out its connectivity, 1, 2, 3, 4, and I subtract 1. So that would be sp3. Lone pairs, it's a little bit, you count lone pairs. So NH3, you count the 3 hydrogens and a lone pair as like, say like one atom, basically. And then you subtract 1, so this is sp3 also. Does that make sense? So in this case, you only have like 3 connectivity, is the way I look at it, so it'd be sp2. Is that cool? Okay, so next question is which compound absorbs at the shortest wavelength highest energy in the UV spectrum? So wavelength and frequency are inversely related if you've taken physics. So frequency is higher energy and wavelength is lower. Higher frequency is higher energy and lower wavelength is lower. Higher wavelength is lower. Yes, thank you. They're opposite. Yes, that's what I'm trying to say. Yes. Let me write it down. Let's put it out on paper. Frequency, high frequency equals energy, and then frequency. This is the sign for wavelength. Does that make sense? If frequency is high, energy is high, or goes up. If frequency goes up, wavelength goes down. So my higher wavelength, the more stable I am. And, okay, yes. I don't know why this is like blowing my mind right now. Lower energy should be higher wavelength. Yes, more stable. Good. Yes. You say longer now? We're putting more? Yes. Yeah, you're right. Okay, we're gonna move on. Okay, so we're looking for the highest energy. So the one that has the least conjugation. Does that make sense? So basically the less stable. So which one, let's do one at a time. So in this case, this has conjugation just with this double bond. So it has just a pair of conjugation right there. So I'll just put 2. Does that make sense? In this one, I don't know, do you guys do cross conjugation at all?
That works.
You guys do cross conjugation?
Well, I mean, it's conjugated, skip, conjugate. Well, double, skip, double, so it's conjugated.
Yeah, but did you guys, good, yeah, this is 2, so this is conjugated with this one, but the difference between this one is actually more stable than this one because this one's cross conjugated. I don't know if you guys reviewed that. For conjugation, they just have to be a single bond apart. So if there's resonance in this case, they have conjugation. Is that cool? So it's just a single bond. The cis and trans S-cis is all like Diels Alder stuff. But we will get there too. So, but yeah, don't worry. So yeah, we're just looking for a single bond, double bond, single bond, double bond. Okay, so in this case, I don't know if you guys reviewed cross conjugation. It's a little different than conjugation. In this example right here, all 3 of the double bonds are participating in resonance together. No, we shouldn't talk about this at all?
I've just never seen that.
Yeah, let's let's not talk. This line just me underlining it. That's not part of a structure.
Yeah, I know.
Oh, okay. Oh, oh, the cross. Okay, let's not talk about that then. Okay, so in this one, this has 2. This one also has 2, right? 2 isolated pairs of conjugation. And then this one has conjugation across. Is that cool? So this is a lot of conjugation, so it involves 3 double bonds. So which one would have the shortest wavelength, so the least conjugation? Because we're looking at, good, so we're looking at A. Is that cool with everyone? Yeah, probably shouldn't even talked about all that conjugation stuff. Least conjugation, yes. So more conjugation, more stable I am, and then I would have a higher wavelength.
Okay.
Does that make sense?
It's lower energy.
Yes.
Okay.
Okay. We're done talking about this one. Unless you guys have a question, then we can stop and talk about it. Does anyone have a question?
We're just assigning 2 points, say, for 1 double bond.
Mm-hmm.
Okay.
Yep. We're just seeing how much resonance, basically.
What was the 2 plus 2?
Yep. So there's a double bond conjugation by this 2, with these 2 double bonds, and then these 2 double bonds together have a 2. Does that make sense?
Yeah, so would C and B be like the same? Like saying like there's 4
Yes. C and B would be more similar because when this one goes to participate in conjugation here, it's not participating with this one. So only one at a time can actually participate in conjugation. In this one, all 3 can participate together if you want to draw the resonance structures. That's why I put 2 plus 2 versus 3 together.
So does that make C and B more than D? Because they're 4 if you add them together?
No, D should have, because if the more conjugation I have together, it would be more stable. So it'd be D. If I was doing the opposite, which would be highest wavelength, lowest energy, it would be D, would be my answer. Does that make sense? And then probably, I don't think they're gonna ask you to rank it. It'd probably be C and B though. Just because of substitution. But they probably will not ask you to rank it like that. That's pretty close. Are we good with this one? A little bit? Yes. I'm just gonna take it away. We good? Okay, we're moving on. I'm sorry for bringing that up. That question was. All right, so this is a review of acids and bases. ACS likes acids and bases. They really like this stuff. So if you didn't understand it before, you're gonna understand it now. So the easiest way, I think, to approach this is to just draw out the example that they usually give right before. So they just do a basic acid-base reaction. So HA plus B, my lone pair, acid, and then I'll be A minus, and then BH would be my conjugate base. So this is your basic acid-base reaction. So I'd have my base taking away my proton, and then my lone pair going off onto my A. So in this case, a Bronsted-Lowry acid, Bronsted-Lowry and Lewis acid are basically the same thing. They're just talking about different things. So they're not the same thing. Okay. So Bronsted-Lowry is talking about protons, while Lewis stuff is talking about electrons. So in this case, a Bronsted-Lowry acid is the one giving away a proton. Good, so it's a donor. And then the Bronsted-Lowry base is accepting this proton. In this case, a Lewis acid is an electron donor. So see, my electrons are being given. Wait, no. A Lewis acid is accepting these electrons. Yes, electron acceptor. My base is the one donating. I just mixed up the order. All right. So relative acidity can be analyzed by comparison of conjugate base. And the stronger acid will have more or less stable conjugate base. Good. More. Nice. And my 4 factors are that fun acronym. Atom, resonance, induction, what's up, Alex? And orbitals. So for orbitals, sp is more stable than sp2, sp3. Usually don't have to go that far into it. I don't know if they'll do, there's an exception to this rule, which is the difference between this and stability for conjugate bases. This one is more stable, H2 negative. In this case is an exception. They do like throwing out exception on the ACS, so this may be useful to note. Is that cool? All right, so sp would be more stable. So my conjugate base, looking at it, in this case would be actually a good example. My sp, this is an sp orbital, is actually more stable than my atom. So that's where it takes precedence. But yeah, usually you don't have to go all the way down to orbitals to find out which one's acid, but this is the orbital exception. It's stronger in this case. Good question. Okay, so now we're gonna do some examples that puts it all together. Okay, so which of the following is the weakest base? Weakest base would be the one that is least able to donate my electrons. So the ones that's not good at donating electrons is going to be my weakest base. Okay, so least able to donate electrons. Okay, so in this case, let's just look at this. Is NH2 an activator or deactivator? Good, activator, right? So this lone pair, instead of going out and acting like a base, is too busy hanging out with this ring. So not a good base because my lone pair is doing something else. Is that cool? So in this case though, once again, it's being activated by the ring, or the electrons are activating the ring, and then my nitrate group is also adding to this takeaway effect by giving it another place to go. Yeah. Did I say activator? Oh, sorry. Yeah, this one's a deactivator. So this is taking the away electrons more. Okay, and in this case, even more deactivator, so it has more places to leave, right? So this lone pair, all these lone pairs are examples of not good bases, because I want my lone pair to stay there. I think my friend gave an example of like, if Girl Scouts come by and you don't have any, if you're not there, you can't donate your money, you know? So that makes sense if you think about it. If you actually maybe don't think about it, it'll make more sense. So in this case, my lone pair cannot donate to anyone else because it's too busy hanging out with other people. Is that cool? So it's not a good base because I want my lone pair to stay there so I can go attack stuff. Okay, so in this case, my lone pair is localized, which is the word, localized. So this is gonna act like a good base because it can go out and attack stuff. So which is my weakest base? It's probably gonna be which one? Weakest would be D. So between, we're going for weakest base. Yeah, I kind of led you in a weird direction. So activators would be stronger bases. If there's activators on the ring, yes. If there was a deactivator, this would be a, deactivators make a ring more, make that proton more acidic. So if I had, in this case, let's say if I had deactivators make this proton much more acidic. This is probably not the best example, but that proton the more deactivation I have on the ring, the more that other proton is going to be more acidic. Does that make sense?
That makes it a strong conjugated base.
It's more stable.
More stable base.
Yeah, more stable conjugate base. Good. Because they can participate in more resonance if you really want to get into it.
So this one would be the most stable base.
Yeah.
This is the weakest.
Yes.
Okay.
Sorry?
So activators are like those are the like if there's no different.
Yes. Good. Good question. All right, so on to, we still got one more. So rank the following order of decreasing acidity. So when we talk about acidity, first thing we do is look at conjugate base, right? So let's just do a quick thing. So when I say conjugated base, I mean after it's donated its proton. So this is going to be CH3, O minus. This one be CH3, OH, just regular methanol. This is going to be CH3 negative charge, and this is going to be just amine. Okay, so we're looking at stability of the conjugate base. These are all my conjugate bases. Does that make sense? What do you think is more stable? Something that has a charge or doesn't have a charge? Doesn't have a charge. No charge, right? So we don't want to charge at all. So between these two, these are probably going to be in the back of my list. Oh, decreasing acidity. So most acidic would be, okay, still good. So these would be at the back of my list. Does that make sense? So let's go between these two. Which do you think is more stable? Methanol or this amine group, conjugate base-wise? Good, methanol. Methanol would be my most stable, so 2 would be in the front, so it should not be A and C. Between these two, which do you think is better at holding a charge, oxygen or nitrogen? Good, so yeah, oxygen, I think we reviewed that again. So this one would be 1, so it should be B. Is that cool with everyone? This one, these two? Which one's just better at holding a charge? Because we're looking at conjugate base stability. So when we do that whole REO stuff, we first look at the conjugate base. So we deprotonate our acid, look at its conjugate base, and then apply this REO thing. So the more stable it is, the stronger my acid. Does that make sense?
Why is methanol important? Like, is it the atom?
Yeah, the atom is better at holding it. Yes. More acidic, it's more of the stability of the conjugate base. So let's look at the classic HCl. This is a very, very strong acid, right? So this bond between them is very weak. So this chlorine's down to leave as soon as it gets in water. So what you form is this chlorine with this negative charge, and chlorine is very, very stable once it gets this negative charge. So my conjugate base, which is chlorine, is a great conjugate base. It's very stable. It wants to leave. It wants to go away. So that's what makes it a good acid. Does that make sense? Stable. So if I have a charge on a molecule, I'm a little bit more stable or unstable, because if I'm holding more electrons than I'm used to, I'm not as comfortable. Does that make sense? So that's why I immediately choose the conjugate bases without a charge. Does that make sense? Okay, cool. Good question though. That was really good. Okay, so we're all good with this one? All right, let's move on to the next page. Does anyone have the time? Just so I can. Okay. We're at question 15. I think. Let me make sure. To make sure we're at like the good spots. We might have to speed. I thought I put the timing after it. All right, I guess I didn't put times after it. All right, we're good. Okay, so let's rank the following in order of increasing acidity. So once again, look at the conjugate base. So we'll deprotonate everything. So this would have a CH2, CH3, negative charge. Is this stable? No, probably not. So this is probably gonna be in the back of our list. So we can eliminate B. Between these two, it has, let's say, deprotonated negative charge. This one participates in resonance with 2 carbonyl groups. So that's good. So going back to our ARIO thing, if I wanted to compare these 3, negative charge, the negative charge is on the carbon, so I have to go to resonance. Between these two, this one has more resonance than this one, so this one's more stable. Is that cool? So it's going to be 2, probably is going to be our first one because it has resonance with 2 carbonyl groups. So whatever doesn't have 2 is going to get eliminated. So by default, our answer choice is C. Is that cool with everybody?
Why did you take? I'm sorry. Why did you take that one as the least stable?
As the least stable?
Or increasing the most stable? Sorry.
Why is this one the most stable?
Yeah.
So this lone pair, going back to this list, can participate with resonance with 2 carbonyl groups versus 1 in every other case.
Well, so why wouldn't we get rid of the H in the middle? Why wouldn't we get rid of an H on the end, and then it wouldn't be stable?
Which is our most acidic proton? Do you remember alpha carbon chemistry? The special stuff with alpha carbons? Or so like how this proton is very stable. So we had a whole chapter on reactions dealing with this one, with aldol, condensation, collision. It's okay. It's a lot. It all gets mushed together. But this proton is much more acidic than normal because it can participate in resonance once that lone pair is. So going back to ARIO, that lone pair is very stable. The conjugate's stable. So that's the special part about it.
Is that the same thing with 4? Like, wouldn't you take it off of another, like the alpha group? Wouldn't you take the hydrogen off the alpha group and then?
So if I took off, let's look at this. Good question. So if I took off a hydrogen off my ethoxy part, let's say if I just took it off, maybe, which one do you want to take it? This one carbon or this carbon? Does it matter to you? CH2? Okay, let's say I have a negative charge here, right? This lone pair is not going to participate in resonance with my carbonyl group at all. So that's what makes it not a good acidic proton. So that proton is probably not going to leave at all. Does that make sense? But this proton, if I got rid of it, make this a CH2, negative charge, this one can actually participate in resonance, so it's more able to leave. Does that make sense? So if I was to do a pKa thing, see which proton is more acidic, which one will leave, it's going to be my alpha protons.
Why is the ketone more stable than that? I mean, more acidic than that?
That one, between 3 and 4, if I had to guess, if these were both negative charge and this was getting delocalized, I'm guessing our oxygen would. That's what I would think at first, but oxygen may be not electronegative or maybe too far away. If I were to do another resonance structure of this one, let's see. If I do something like this, this would have a negative charge, right? So I think I don't know the actual answer to this, but my assumption is that 2 negative charges on one molecule is not great. Well, this one, that's why this one, yeah, honestly, that's a tough one. That's what I can think of right now, but the 2 negative charges are probably why that one's more stable than the other one. No problem. That's a good question. Okay, so next one, oh, sorry, what's up?
What if we add an aldehyde ester? Will the hydrogen
If I had what kind of ester?
Aldehyde ester.
Aldehyde
Yeah.
ester? Would it be more acidic than which one?
The C2, the metonic ester.
This one?
Yeah. There's been one which in the past the exam.
Uh-huh.
I selected this one, but the answer was that aldehyde ester was more acidic. But I didn't know the reason why.
Is it the acetoacetate or acetoacidic ester?
I think so, yeah.
Was it that one? Let's see. Is it like that? Or, wait, no, that's not right. Oh, okay. So like that. Why would this one? So the answer was this one. Let's see. Proton wise. So it could be kind of going back to this example. This oxygen can sometimes donate part of resonance and make this negative. So then you have two negatives on the ring at some point, and that would make it a little bit more unstable compared to just one of them doing it. That one you may have to ask Dr. G, because like I am not sure, but that's the only explanation I can think of right now. Drawing the resonance structures does help, because that's the only reason I knew this could have two negative charge. So that's what I would think of, but that's a good question. Yeah, at some point it probably wouldn't go into that, but yeah, it's a possibility. That's very unstable. Yeah. So maybe that's why this one's a little bit better. That's all I can think of right now. Okay, so let's move on to 16. We're all good with that one? Okay, so which sets of hydrogen atoms in the compound below will undergo deuterium exchange with that thing in the presence of that thing? My naming's not my best quality. Okay, so for this one, all it's saying is which are my most acidic hydrogens. Because once my hydrogen leaves, what do we have? A negative charge, right? So if there's a ton of deuterium floating in around in solution, it's going to go get attacked by the negative charge, and it'll be attached to it. So if I were to draw what that looks like, say if I had carboxylic acid, and it just lost its proton because it's an acid, it has its negative charge. And if I had just deuterium floating around, it could just attach to it. And that's my next structure. So all it's asking is where are my negative, or where are my most acidic protons? Is that cool? Okay, so my most acidic protons are right here, because this can participate in resonance, and then also this one. So basically, where are my alpha protons? So 2 and 3 is not an answer choice. Oh, it is, thank goodness.
Why wouldn't the end, since it's ethyl sodium, why wouldn't the ethyl on the end of the oxygen group
This,
on the right?
oh, this one?
Yeah. Why wouldn't that whole section? Oh, we're just looking at the proton now?
Yeah, because deuterium.
Why is it ethyl?
So the reason they put the
Wouldn't it
ethyls,
say that it was methyl oxygen deuterium?
the reason they put the ethyl groups is because this could also react with this part and kick this off. Do you remember?
Yeah, so wouldn't that make that also, if that was replaced with the other one, oh, there's no deuterium.
Yeah, so the question is just asking which sets of hydrogen atoms will undergo deuterium exchange. So yeah, what you're saying, it will react weird, but the question is just asking about hydrogen atoms. Does that make sense? Okay, so let's go on to 17. Rank the following compounds in order of increasing acidity. We've done so many acidic problems. Okay, so what do you guys think? Rank the following compounds in order of increasing acidity. So least acidic to most acidic. Which one's going to be my most? Oh, between oxygen, this is sulfur. So periodic table trend. If say this was my periodic table, like this, the acronym is BEARS, which is going to help you if you're taking the DAT or MCAT or something. So B, E, A, R, S. So these are all my periodic trends. So acidity, which is my A, it goes all the way to the right and down. Does that make sense? So same with basicity goes that way. So the stronger acid is going to go right and down. So between sulfur and oxygen, which one is lower on the periodic table? Sulfur, right? So the larger I get, the more acidic I get. Is that cool? So between these two, which one's going to be most acidic? Or which one's better able? Good. So sulfur is going to be one that's better able to hold the charge. It's going to be more stable. So it's going to be 3. And it's going to be then, what's going to be my next one? Good. So 1, 2 sets of resonance. And then 4. Oh. What if I did that? Boom. Game changer. 4, and then last but not least, 2. Is that cool? Yeah, sorry, I didn't mean to do that. I was too stubborn to change it. Wait, sorry? Oxygen. Yeah, so this oxygen would be more electronegative, but because sulfur is larger, in this case, that effect takes precedence. Does that make sense? Because it's farther away. Yeah, sorry. Okay, cool. So on to the next one. We might speed it up. I don't know how I'm on time. She said I had like a decent amount of time.
40 minutes.
We have 40 minutes? We're probably gonna go over. You're welcome. I'm just kidding. Sorry. Okay, so stereoisomers. We'll fill in the blank. So, I just gave the answer for the first one, stereo. Isomers have the same connectivity of atoms but different arrangement in 3D space. All right, so what are enantiomers? They are non-super imposable mirror images. And have identical or different physical properties. What do you guys think? Good. Very confident answer. Yeah, so they'll have different properties and differ in the way they rotate light. So rotate plane polarized light. Okay. Diastereomers are stereoisomers that are not enantiomers. Okay, so when is a compound chiral? When it has a non-superimposable mirror images. So I think your book tells you what usually works most of the time is, does it have 4 different things it's attached to? That works most of the time. This one is the universal rule, basically, when it has a non. Okay, does that make sense? All right, so we're going to do some practice. How's everyone feeling about chirality? We should be feeling good. So the main rule for this one is, if my lowest priority is not on a dash, then I have to flip the stereochemistry. Does that make sense? So it'll make sense when we do a practice one. So let's go by priority. Priority is based on atomic number, okay? I think in SI I said molecular weight. I guess they're the same. They're not the same. So priority equals atomic number. Is that cool? So in this case, we'd have 1, 2. So the way to do this is, if I'm comparing these two, I look at the 3 things it's connected to. So this carbon is connected to another carbon, and a hydrogen, right? And then this carbon is connected to an oxygen, If it's attached to a double bond, it counts as another oxygen and another oxygen, because right there. You only have to look at the first one. If it gets beat in the first one, then this one takes priority. So like this carbon, oxygen, oxygen, higher atomic number, right away this one takes priority, so this is my good one. Is that cool? So this is going to be my 2, this will be my 3, this will be my 4. So what way is that? But then what I do, because my lowest priority is not, flip that, so R, good. Okay, so this one's going to be R. So let's do this one. So once again, 1, 2, 3. It's going to go this way, so S, and because my lowest priority is not on a dash, R. Is everyone good with that? Okay, so next one. 1, 2, 3. Why did I put D as like the S? Because now I just had to do all of them. Okay, so 1, 2. Oh wait, I lied. 1, 2, 3. Wait, was that right the first time? 1.
Pretty sure the sulfur is more than double the oxygen.
Yeah, so this should be 1, 2. Oh, we're looking for S. Yo, I thought we were looking for R for a second. I was like, where's the answer? Okay, so this one's S, right? So that's the answer. Wow, that was weird. Okay. You should get sleep. Sleep helps for finals, surprisingly. Okay, so 19, what is the correct stereochemical description of the relationship between this pair of molecules? Can you guys hear me okay? Which I probably should have asked an hour ago. Everyone can hear me? Okay. Okay, so for the way to tell if it's an enantiomer is if the chiral centers all flip. So if, say, if these ones were all S, my structure should be all R, my next one. If only one flips and not all of them, then it's a diastereomer. Does that make sense? So if they don't all flip, it's not an enantiomer. That's just the quickest way to tell, in my opinion. So let's look at my chirality. So let's do my priorities. 1, 2, 3. So this is going to be R. And then 1, I'm doing this one now. So 1, 2, 3. This one is also R because, so this is S originally, but lowest priority is not on a dash, so this is also R. So we got 2 R's. So this one's going to be 1, 2, 3. So this is S, because originally it's R, and then we flip it around because same thing. Okay, so now let's do this one, which is 1, 2, 3, S. Yeah, and we don't have to flip it because my lowest priority is on a dash. So what are these guys? Good, good. Nice guys, enantiomers. Yes, in this, if the connectivity is the same. Yeah, so if this was RR and this was SR, diastereomers. If none of them switched, but different connectivity, constitutional isomers. Is that cool? Okay, so for constitutional isomers? Oh wait, do we do those with chiral centers? I think they could still work, it's just different connectivity.
I thought we would look at the wedges and dashes, and if all but one, if all of them changed,
Mm-hmm. Enantiomers.
that's an enantiomer. But if all but one changed, it's diastereo.
Yeah. If something sounds weird, please tell me. Or feel free to look it up too. And then because I do make mistakes. I'm human. Okay, so moving on to the next question. Okay, so question 20. Ooh, we're halfway there kind of. So which of the following are optically active? So is this optically active? Is this a non-superimposable image? And what I mean by that, if I were to draw this, so it does have a non-superimposable image, as in like it's a mirror image, but is it optically active? This is kind of like a trick for ACS. It's actually not optically active because of, so this is chiral, but it's not optically active. Okay, so chiral, yes. Optically active, I'm just gonna put OA. No, because of something called nitrogen inversion. Okay, so brief thing on that. You know, you can have a solution of just the R product and just the S. You can't really isolate a nitrogen chirality center because these will keep flipping around. So inversion-wise, if these carbons and these carbons are always moving around, I can't just isolate an R or S, basically. So that's nitrogen inversion, unless these are too bulky. That's something else. But, so yes, it is chiral, but it's not optically active because there is no like RS chiral center. So 1 is not the case. This is like one of those things that ACS might throw at you because they're kind of annoying. Okay, so 1's out of there for 3 of them. So now we're between 2 and 3. What about 2? 2 is no, right? So there's symmetry. These are not even chiral. So I don't even, is it? Does meso have to have a chiral center? I just don't remember the definition of, like a meso compound. Does it have to have a chiral center? Okay, so yeah, I guess it has to have a chiral center, but if it's symmetrical, then it's a meso. But I don't think this isn't a chiral center because these are the same. Yeah, so this one's just not chiral. Okay, and then what about 3? So this is one that one of those ACS might drop it on you type questions. This is chiral, kind of going back to like cumulated dienes. Do you guys remember that stuff with a double bond, C, like there's no conjugation, like they're dienes, but they can't really move around. If you look at the structure with the p orbitals, p orbital here, p over here, and a p orbital here. So orbitals are electron clouds. If these clouds are so close to each other, like they're both pointing up, it's going to be interacting. So say this is one carbon and another carbon, and then my arms are my p orbitals. If they're like in hindrance with each other, this is like very not comfortable. So one's going to go like this. Does that make sense? So because one goes like this, it kind of makes a chiral center, weirdly. So like say these 2, chlorine and hydrogen, would go up and down, and this methyl and hydrogen would go like this way. So it's making kind of like 4 different substituents on a carbon. It's a weird concept, but we may have gone over this actually last day. But yeah, in this case, this is a chirality center because this is basically seeming like 4 different substituents. It's one of those that actually do pop up on the ACS, so that's the fun stuff. If it's optically active, it rotates light. So so R is clockwise, right? So if I had a solution of just like an R isomer and I place it in front of this light source right here. So I have this line of light, it's gonna rotate this line clockwise. So that's what basically optically active is. If it doesn't rotate it like this line, it just stays straight, then it's not optically active. Does that make sense? Cool. So that was a quick, brief
So optically active doesn't mean it has color. It just means it bends light.
Yes, it has rotation. It's chirality. I don't know about color though. Not to say it doesn't, I don't know. I know conjugation has to do with color. A lot of conjugation between something.
Because wavelength is color.
Yeah, so if it has like between 400 to 750 nanometers or something, I think it's color. But yeah, good relation. Okay, so E2. This is a throwback to Orgo 1. So the brief mechanism of an E2 reaction is if I had a, let's say, bromine, hydrogen, and then I had an OH group. Take away my hydrogen, this turns into a double bond and then kicks it out. The key thing with E2 is that these two groups should be anti to each other. Is that cool? Anti. If they're not anti, it doesn't work because it's the backside stuff. You know? So same with S and 2. Hitting it from, we're going from the backside. I'll phrase that better next time. So yeah, so we're looking for something like this. So is this something like this? No, this is sin. Same side, so this is not A. I don't even know what this is, because that's not it. Is it, whose man is this? It's not D, it's B. That looks more similar, right? So that's E2 mechanism. Is that cool? So loud. Okay, so let's draw all possible products of dehydrohalogenation of the following compound. All right, sorry for stuttering, guys. It's just gonna happen today. Okay, so we have OH, basically testing what we just learned. I'm gonna draw my other hydrogen here, and I'm gonna draw two of my hydrogens here, and then my other hydrogen here. So which hydrogen out of these three is actually anti to my bromine? Is it this one?
Oh, the one on the left, the wedge H.
Good.
Not the wedge, the dash.
Yeah, good, the dash. Bless you. Yeah, so the dash one's the only one that's actually anti, so my OH is the only one it's going to touch is this one. And so it'll just form double bond and then CH3. And that's my only product. Is everyone good with that? So this is a review of E2, all that stuff. Okay, next question. All good? Okay, cool. Predict the major product when the following compound is treated with hydrobromic acid. All right, so we know it's substitution because all our answers are only substitution. So look at that. So your answer choices are giving you answers. That's supposed to help. Okay, so knowing that, we have a pentane ring and we have a butane, cyclobutane. So the fact that this alcohol is secondary and we have substitution, do you think it's going to be SN1 or SN2? SN2 or SN1? SN1 actually. Sorry? Well, because it's HBr, the H will protonate the alcohol, turn into water, so eventually make a good leaving group. SN1 reacts fastest, or SN2 reacts fastest with primary, secondary, tertiary. Does that make sense? So SN1 is actually the one, if you see tertiary, if you see either secondary or tertiary, sorry, this is a disaster. It's usually the one that predominates if there's secondary, SN1. Yeah, because it forms a carbocation. So anytime you see SN1, you know it's going to form a carbocation. Draw out your carbocation structure, because the ACS really likes the rearrangement stuff. So yeah, anytime you know it's SN1. I'm so dumb. I drank all my water before getting started. Okay. Take that with me. Okay, so in this case, we're going to draw our carbocation immediately once this leaves, right? Because alcohol is eventually going to turn to water and it's going to dip. Okay? So one option I could have is just the carbocation staying there and eventually just having this. Right? That could be one. So this is if, so is this secondary one that stable as a carbocation? Is there a more stable way?
Methyl shift it'll make them stable.
Good. So there's two places where I could have a methyl shift. So I can either shift this methyl group to that spot, and then my carbocation would be here, or I could shift this one and change my whole ring structure and make a connecting thing here. It's a disaster. All right? But which is more stable, cyclobutane or cyclopentane? Right? I made sure to do this one before class so I can actually look at it and not like be terribly confused with my numbering. So for this one, the best way to approach these rearrangements is to number your ring, okay? So let's start with the terrible one first. So I'm gonna number this carbocation 1, okay? And I'm gonna number this, the one it's connecting to 2, okay? You can number it however, this is the one that works easier for me. 3, 4, 5. So I have 5 carbons numbered. I'm just gonna now draw out my cyclopentane ring, okay? So basically this carbon right here is opening up and attaching there, okay? So now I have this ring. So I know the connections between 1 and 2. So let's number my ring again. 1, 2, 3, 4, 5. Carbon 1. Yo, this was twisted the whole time? You guys, you guys can tell me to like adjust it. Okay, so I know 1 has this methyl group, so I just add this methyl group. And I know 1 and 2 just got connected to each other. I know 5 also has a methyl group, right? So now I just put my methyl group there. If you notice before, this carbon that was initially attached to 5 is gone. And carbon 5 doesn't have any hydrogens, so that's where my positive charge is going to be. Does that make sense? So, since my positive charge was there, that positive charge will eventually get attached by bromine. Does that make sense? So, moral of the story is number your ring, and it makes it so much easier. So do we see that anywhere? Would you look at that? B. Yay. This is practice, I think, to be able to see that easier, because I didn't really see that at all.
We didn't do that kind of methyl shift.
Really? I think you, with cyclopentane and cyclohexane, I think. I'm in your, oh wait, for Orgo 1 or Orgo 2? Oh, I was like, we're in the same class right now for Orgo 2. It's like, what do you mean? I feel like that's not to like rag on Orgo 1, but this is something we should have done a little bit more, because I know ACS likes their carbocation rearrangements. Is that cool? It's probably not that cool. But on to the next one. Which substrate, I think I have another example. If we have time, we'll hit that again. Okay, so which substrate is most reactive towards solvolysis? All this is asking is, which is basically a loss of a leaving group. So which is my most stable leaving group? Okay, so once this leaves, once this iodine leaves, I just have a positive charge. Okay, so that's all solvolysis is. So it's asking about that positive charge that is formed once iodine leaves. So I'm going to take away my iodine. So looking at this, is a vinyl carbocation stable? No, so this is probably not going to happen. Is, once again, another vinyl carbocation stable? No, not going to happen. This is primary, not really that stable, but this one is conjugated, and this carbon's called a allylic. So this one, or you can call it the benzoic or whatever. So it's allylic, tertiary, secondary, primary. For carbocations? Oh, no, sorry. Yeah, so this stability with carbocations. I think methyl. I forgot methyl. Is that cool? Is this confusing people? That one. Sorry? Yeah, carbocation. So soluble lysis, it's just asking about the leaving group and the carbocation. Okay? We're all good? Moving on. 25. Okay, so this is a quick one. Which of the following is most reactive towards nucleophilic acyl substitution? This is all with the carboxylic acid derivatives. Which is my most reactive? Yeah, the acyl chloride, acyl halides. So where's my only acyl oh, what do you guys, no one tells me anything. You guys, what? So which is my only acyl halide? E, good. So yep, boom, done. That was easy. We're all good with that question? We're doing 25. It would probably be easier to keep up if someone told me to move up the page.
Do that order. What was it?
It was anhydrides. Was esters next? Esters and amides. Cool. I think carboxylic acid is somewhere in between this one, right? These are all derivatives, so that's why it's not on the list. But reactivity-wise, I think carboxylic acid, so look this up. Hmm? Yeah, I think it's, like you said, like ester. Yeah, it's either the same reactivity as ester or like between those two. I would look that up because I'm not too sure. Oxidation reduction. I feel like a lot of people come out of orgo and chemistry not actually understanding oxidation reduction. I could be generalizing because that was me, because I never understood it till like some time ago. The easiest way to approach these questions, you can find oxidation states, and I'll go through that in a second. But for me, the easiest way is for oxidation to tell if something's either oxidized or reduced. If it's oxidized, it will either gain oxygens or lose hydrogens, okay? So if I was reduced, I will either gain hydrogens or lose oxygens. Does that make sense? It's just like a quick way to see if I was reduced. So we're asking what type of reaction is this one? It's a reduction. So do you see I just gained a hydrogen, and I gained two hydrogens. And fun fact, if you see FADH2, NADPH, all that stuff you probably forgot and you'll see in biochem, that's in the citric acid cycle. When you see that stuff, all reduction, like think oxidation reduction, if you see NADH, NADPH, all that stuff, you know. That's more biochem related. You probably don't need that right now. We will, yeah, we should review oxidation states actually. So let's look at this one. When I talk about the oxidation state, I just look at this element and compare it to the one it's attached to, and whatever is more ionic is the one that's going to hold all the electrons. Okay, so I have 4 electrons in this bond, right? Nitrogen keeps all 4, and carbon doesn't get any. Okay, so I think I do valence minus how many electrons it actually has after it's ionized. So in this case, this carbon right here doesn't have any electrons in its double bond, but it shares covalently with this carbon one. So it has one right there. And also it shares another one covalently with this carbon, right? So that's 2. So 4 minus 2 is 2, right? So this has an oxidation state of +2. Cool stuff. Let's look at this carbon. So this carbon doesn't take any from the nitrogen, doesn't take any from the nitrogen because nitrogen is very selfish. But it has a covalent sharing thing with the other carbon. So it has an oxidation state of 4 minus 1, which is plus 3, right? So now let's look at this carbon again. Let's see how it changed. So now it actually, this carbon, nothing changes with the nitrogen. Oxidation state stays the same because it's more electronegative. But in this case, this is going to be 4 minus 2. So now it's plus 2, right? So it gained an electron because my number just went down. And about this one too, let's look at it. And now it has 2, right? 2 electrons because they share these electrons. It also has another one sharing with this. So it's 4 minus 3, right? Plus 1. So this one was also reduced. Is that cool? So now we're somewhat understanding oxidation reduction. Yay, so this one's D. We're all good? Okay, so now let's look at 27. Which reagent will accomplish the following transformation? Just looking at it, I don't know what these are. So I don't think we did anything with that stuff. Between Grignard and the copper something something, which one is a stronger reagent? Grignard, right? So where do you think that's going to react? Good. So Grignard is probably going to react to my carbonyl, right? So this is a positive, slightly positive area. This is also a slightly positive area. So because this is too strong, it's going to react to the carbonyl. Gilman is the reagent. It's a little weaker, so it'll attack here. Yay. I'll give this one. On to the next one. Yeah. Okay. So draw the major product formed when benzene is reacted with. That was so ugly. Benzene reacted with 1-chlorobutane AlCl3. Is that cool? So basically all this is forming is this reagent right here. All it's forming is this carbocation. But when I say carbocation getting formed, think rearrangement, right? So I'm going to have I have 2 hydrogens here. I have a hydrogen here. Here. So this is going to shift to something more stable. 1, 2, 3. 1, 2, 3, 4. Wait, did I draw something wrong? The plus should be. Oh, right here? On this one? Oh, thank you. I don't know why that was not coming in my head. Okay, so now it's going to attach to that one. So whenever I see carbocation, let's definitely draw that rearrangement, or draw it out so you can see if there is rearrangement. Oh yeah, sorry, I kind of did it in the corner. Yeah, so hydride shift, hydrogen there. Okay. Next question, we're all good? Okay, so which set of reagents would most likely convert toluene to the following compound? What's the only way I know how to, first of all, what's toluene? Does that make sense? Everyone good? What's anisole? Sorry. Yeah, methoxy. Yeah, I think, anisole's methoxy one. Yeah, I think that's what got everyone on that one test. Sorry guys, I'm just bringing up bad memories. Okay, so what's the only way I know how to brominate a ring like that? Not this radical reaction, not this one, this is chlorine. This one, I forgot what that is, I'm just gonna be honest. And then C, that's the way to do it. Which one is this one? Oh, really? Okay. There it is. Thank you. Yay. Someone's, you're going to do well.
I don't understand why we have to use iron over
So,
light. I guess that's my problem.
okay, so like the ring, the benzene ring, is it reactive in general? No,
Yeah,
right?
but methyl is a slight activator, so
Slight activator. My benzene ring's really stable. So all this reaction with the iron bromine makes it much more electrophilic.
doesn't carbon and chlorine do that as well?
But I'll add chlorine instead of a
I
bromine.
mean, no, D.
D? No, not C. Because this carbon isn't, it's not a metal. So that's where the iron is a really positive. You gotta really, like she's saying, really dig it in. All right, so 30, draw the polymer from the following monomer. This is something we barely touched on in Orgo 1, but this is actually really easy, which is the good part. So let's just draw it out. So C, double bonded CH3, CH3. Right, so CH2. So addition, polymerization is awesome because it's easy. So all I'm going to do is I'm going to redraw this without the double bond. Okay? So I'm going to draw my brackets. And I'm just going to redraw C. I'm just going to face my CH3s down. You can face them up if you want. It's up to you. I'm going to draw it without the double bond. H, H. And then close my back brackets, and all I have to do is just draw a line outside. Boom. Polymerization. Sorry. Okay. Is everyone good with that one? Okay, cool. Okay, so let's do this one. Does anyone recognize this one, this molecule? If you get it right, you get to do well on your ACS. It's fat. It's triglyceride. You don't need that on the ACS. I was kidding. Huh? Is it a what? Glutaric acid? I don't know. I'm not good with my common names. You're probably right, but I don't know. I'm sorry. Okay, so we're having sodium hydroxide with water, right? NaOH, which is hydrolysis. When you have a carboxylic acid derivative that goes through a hydrolysis, you usually just break apart right here. Or do you break apart right here? Does that make sense? So hydrolysis, usually the next step is adding, like a second step would add like water so I can protonate. But I'm not protonating it, I'm leaving it as is. So I'm gonna have this O negative attach this CH2, CH3. So if you wanna know what kind of happens, this OH negative is gonna attack it here. Eventually this bond is gonna come back down and kick this one off, the whole classic hydrolysis stuff. This is actually how you make soap. This is saponification, fun fact. So the other thing is that forms is ethylene glycol, which is 3. It's not drawn like that. I guess I don't have to draw H. So that's the other thing that forms. I think the main thing is to know when my carboxylic acids undergo hydrolysis, what happens. So this is what happens. Everyone kind of good with this? All good? Okay. So yeah, this one's saponification. Maybe you've seen this in Orgo Lab, maybe not. Yeah, this is just hydrolysis. There's no heat in this one. So just NaOH and water. Just basic hydrolysis. Heat, it may accelerate the reaction. I'm not too sure. Okay, so next question. All right, so which of the following is the product of aldol condensation? So aldol condensation produces an alpha beta unsaturated ketone, right? So where do you see an alpha beta unsaturated ketone? This is aldol addition, close, but it's wrong. This one, 1, 2, 3, nope. Oh, okay, so yeah, it's not this one. So let's see. I'll go with that one. Okay, so let's draw the product form with benz C. Yep. So next one, draw the product form with benzaldehyde and acetophenone. So this is all alpha carbon stuff. So this is an aldol. I'm just gonna put heat. Let's say it's an aldol condensation. It's going all the way. Okay, so I think this trick is shown in the book. I thought I was like revolutionizing it, then I just read the book and it's like right there. So all you do is you find the alpha carbon. This is the only one with an alpha carbon, or alpha hydrogen, sorry. And then all you do is take that one, and then you take what it's reacting with, and you face the thing it's reacting with towards the alpha carbon. Is that cool? Sorry? Oh, I just added it. If I didn't add heat, it'd go through aldol addition. I'm just going through the condensation product. Yeah, it should say explicitly have heat. So all I do is connect the double bond right there. And that's the alpha beta unsaturated ketone. Does that kind of make sense with everyone? It's just like a weird trick to do aldol condensation really quick. Does that kind of make sense, maybe? So, yeah, so if going back to that chapter with aldol condensation, sorry? Yeah, so this is the one that gets the negative charge and has the one that'll be reacting with this. Does that make sense? So it's the alpha carbon being acidic, and this is just a trick to draw the aldol condensation really quick. I think your book has it too. Okay, so the next one, so that one is this structure. I can draw it smoother later if we have time. Okay, so which of the following is a key intermediate in the reaction below? So HBr, yeah, this should be a peroxide. This should be ROOR. So what determines whether it's going to be, so there should be an oxygen here. So what determines whether it should be on the most, if I'm adding the bromine on the most substitute or least substituted, depends on this thing. If it's a peroxide, it goes on that least substituted. So this is a radical reaction, so my bromine is eventually going to form a radical. This is what this part does. And it's going to react with this one, and this radical is going to go here because radical stability is the same as carbocation stability. So this radical at this tertiary position is more stable than one at the secondary. Does that make sense? So this is like a radical reaction to go over, and just pay attention to if this is a peroxide, because it'll make it go to the least substituted, the bromine. If it's not peroxide or something else, it'll go to your most substituted.
Mark off that and put peroxide there instead?
Yeah, there should be another oxygen between the two. So it should be like, for this one, it should be CH3, CH2, O, O, wait, CH2, CH3. Does that make sense? Like H2O2 type thing. So this answer would be A. Yeah, this is a radical reaction, so carbocation is not formed. And this is also substitution, so no. All right, on to, do you guys have the time? Assume? All right, so we're going a little over, so save questions for after. I'm gonna kind of go like going in, all right? So I apologize if it goes really fast. Okay, so this one is just asking, which of the following produce 1-pentanol, all right? And if you don't have time, this will be posted on YouTube also, and the answers should be up there too, okay? So which of the following methods will produce 1-pentanol? So this is a Grignard reagent. It's pretty strong. So basically this is negative, and this carbon is gonna go and attack this, and it's gonna form an alcohol. So 3 carbons plus 2 carbons. I'll make that 1, 2, 3, 4, 5, 6, OH. So yes, that looks like 1-pentanol, right? Because 3 carbons plus 2, OH, okay? So what is this thing? B2H6. If I reduce 2 and 6 to its like the ratio, it would be good, nice, BH3. What is this? Yeah, what does THF stand for? Nice. No, I'm just playing. It's tetrahydrofuran. So this is THF. Does this look familiar now? Yeah, so it adds an alcohol to my least substituted. So literally the same thing. Good answers, guys. So yeah, that looks like it too. And same with Grignard. 4 carbons right here added to this carbon, making 5 carbons. Grignard will force this up. Then I have an acidic workup, which will protonate that negative charge. So once again, would you look at that? We have 3-pentanol, 1-pentanols. This one, tert butoxide, which is this is not, in general, this is not like a reactable compound with tert butoxide. Like this is usually used for elimination, right? You guys kind of recognize that? You don't really eliminate hydrogens off an alkane ring, or alkanes in general. That just doesn't happen. So this is no reaction. So it's gonna be 1, 2, and 3, okay? So moving on, which of the following will produce cyclopentanol? Just looking at this, same thing, tert butoxide reacting with carboxylic acid. Maybe it'll produce an ester, maybe not, but it's not producing what we want it to produce, so no. This is a hydride, but I think you only learn that it reacts with like ketones and aldehydes, right? I don't know specifically what it does with carboxylic acids, but it doesn't get what we want. That's an ether, so no. This one is a strong reducing agent, and this is a ketone. So ketone is going to get reduced to alcohol. Well, would you look at that? There's our answer. This one will just alkane reduced, or alkene goes to alkane. So this will just be cyclopentane. Cool? All right, so next one. Which of the following DNs cannot participate in Diels-Alder? So for it to participate in Diels-Alder, it has to be S-cis. So S-cis is this. So it must be in this conformation. If it's in a ring, that means it's locked and it can't move. Almost just like spit everywhere. But if it's in a ring, like let's say this, in this case, it's like forced in this S-cis conformation, which is good. For this one, it's good, so it'll participate. But it can't, because single bonds can turn usually. In this case, it can't because of the ring. So it can participate, and we're not looking for that. We're looking for cannot. This single bond can flip over and then go in an S-cis conformation. Does that make sense? So this one's also can. This one, but this one is stuck in his S-trans because of this ring. This bond right here is not going to be moving anywhere. Is that cool? So this one's our answer. This looks a little intimidating at first, but just go back to your base. We have chromic acid is it's something I recognize. What else I recognize is this benzene ring right here, right? So anytime there is a hydrogen off that benzene ring, a carbon with a hydrogen, chromic acid will turn it into carboxylic acid, right? Just everything. If it's a tert-butyl group off your benzene ring, it won't happen because you need that hydrogen. So, C, because there's a hydrogen at each point. Okay, next one is not something you did, right? Dieckmann cyclization. Did you guys actually? Oh, you guys did it? So yeah, this may take some time. The answer is B though. And that's it. That's the explanation for that one. B. I actually never learned this in my class, so even if I want to explain it to you, I apologize. I probably couldn't do it well enough. But I will post later an example for you guys. So next question. Show the starting materials that can be used to prepare the following compound by Diels-Alder reaction. So for a Diels-Alder, we need a diene, which is a 1,3, just conjugated diene, and we need a dienophile, right? So we should have this S-cis diene plus some double bonded thing, usually with a group that makes this double bond more reactive or takes away electron density. So like O-phile, the phile means it wants electrons. These nitrate group is obviously making this double bond want more electrons. Okay, so we're trying to make this compound. Immediately we can take off.
You can cheat on this one because the number of carbons is too many or too little.
Good. So yeah, we can take off a lot because of that. The first one we can take off is A. There's not enough carbons, right? Yes. Yeah. Oh, sorry. Yeah. A has too many or too little?
A is too little, and
Yeah.
B and C are both too many.
Yeah. This would form a bicyclic, right? This is missing a diene in general, so no. So this one would form the hat on top, making it bicyclic, right? Is that cool? So yeah, D. Good. So count your carbons for this one. That's a really good idea. Next, 41. Predict the following reaction. This is another one of the cyclization ones. I don't know if you guys did this. But for now, we're going to skip it because I don't think you guys did it, but I'll look after. Yeah, it was one of those like weird cyclic ones. I just put an X on it, so I don't know if you guys did. Okay, so this is a classic Grignard reaction, right? So this is going to be excess, slightly negative. It's going to come in and attack here. It'll force this up, and eventually this will come down and then kick this one out. I just did 2 mechanisms on 1 molecule. That's not recommended because this looks like a disaster. But just know this O bond right here is eventually just going to break. Okay? So the easiest way to know what my product's going to look like is number my ring. 1, 2, 3, 4, 5. Let's stop right there. I'm not going to go to 6 yet. So carbon 1, 2, 3, 4. So at this carbon 1, let's say this is carbon 1 right here. 4, 5. So carbon 5 is a methyl group, right? Attached to it. Does that make sense? So we have this methyl group right here, and it also has this oxygen attached to it, which got protonated at some point. So now this is also OH, right? It would actually be this group right here that's added onto it, but it won't be a ketone anymore. It should be an alcohol. Yeah, sorry, thank you. Yeah, this is not sorry, this isn't a ketone, because once this goes up, this becomes O negative, especially because the excess Grignard is just going to keep going in and attacking it. So it'll kick it out, then another group will come in, methyl group will keep attacking if there's excess, and turn your ketone into an alcohol, okay? So you'll have another methyl group. So you should have two methyl groups actually. I'm going to redraw this. Two, like that. Say this is carbon 5, OH, 1, 2, 3, 4. Okay, and then two methyl groups should be coming off. And then you should have your alcohol. Does that make sense? This is a 1. This is not a double bond. All right, I give up. That's a 1. Ignore that blob. That's not chemistry. Good? Do you want me to redraw it?
It's too much.
Yeah, so it'll keep attacking that carbonyl. Okay, so next one. This is, I think, chapter 18. Okay, so we're gonna look for our central carbon, which is right there. If you guys remember, this forms ethylene glycol is OH, OH, and then acetaldehyde is just this one, right? So these two carbons are going to basically it's basically just going to attach right there. So if you can find your central carbon, that's all you need to do. So central carbon, this was a ketone before, and this is my ethylene glycol. Probably the worst explanation ever, but this is chapter 18 or 19. It's actually not as crazy as it seems. This is the one that's also a rearrangement, because hexane is more stable than pentane. So it's going to be D. I don't know if we'll have time to do this one right now, but for now, let's just leave that at D, okay? But it's similar to the one we did with the butane. It's really similar. Okay, so we got a few more. Okay. So for this one, this is, if you don't recognize this, it's meta-chloro peroxy something acid, right? Do you recognize that one? MCPBA. So this is Bayer-Villiger, if you guys remember that. And the Bayer-Villiger reactivity, you know how it places an oxygen on one side of the ketone? You guys remember that? And then makes it into an ester. But to pick which one, the reactivity goes in this order. Oh, hydrogen. That's its reactivity. We have pH. Methyl, right? So that's my reactivity. So it's going to get placed on this side, okay? And also, this is an Orgo 1 review. This reacts with alkenes to form epoxides. So heads up, you should do a little review on that. But my final structure is going to look like this one, methyl group, epoxide. So I'll leave that there for a second. All good? Everyone good copying it down? Okay, so next one. Predict the following reactions. So this is brominating our ring. So we just have to find out which ring is more activated, right? So this right here, if a carbonyl is directly attached to a ring, it's going to pull electrons away from my ring. Okay? If there's an atom with a lone pair directly attached to the ring, it's usually a donator. If you look at your chart, that's what you'll see most of the time. So this ring is getting activated while this ring is getting deactivated. Okay, so this is activated, this one's deactivated. So which one's the reaction going to be on? It's going to be on the activated one, so that's why it's A. Cool. All right, spectroscopy. Okay, so smaller atoms give bonds that vibrate at higher frequencies. If you kind of think like you play guitar, you play higher notes, they vibrate faster. Oh, thank you. Wow, that's a first. Okay, so stronger bonds will vibrate at higher frequencies. Guitar strings are very tight if they want to be a higher note, so a very similar concept. And higher wave number. All good? We flying. I apologize for this like rushed last part. This part in your book, I'm sorry. I normally go through and label all of it, but just like check your book, all right, for these numbers, okay? But we can do this one. Conjugated double bonds absorb at a higher or lower wave number than localized pi bonds. They actually absorb at a lower. And this because that they would have more single bond character. Okay, so that means they're basically more stable. Okay, so the intensity of a signal corresponds to the polarity. All right, and the broad signal associated with alcohols and carboxylic acids is hydrogen bonding. There's multiple oxygen-hydrogen bonding interactions it could have, so that's why it's broad. That's your explanation. Especially with carboxylic acid, because there's two oxygens. Okay, so fragmentation of molecular ion generates a radical and a carbocation. The only thing the spectrometer or the mass spec picks up is your carbocation, so the radical gets tossed aside. So the mass spec detects the charged fragment, which is our carbocation. The molecular ion peak corresponds to the molecular weight of compound. Oh, it's already there, of the compound, okay. The base peak is the tallest peak, and it corresponds to the most abundant or most stable fragment. Okay, so now the base peak is always, sometimes or never, the same as a molecular peak. It is sometimes. Base peak is not always your molecular peak. Okay, so this has to do with homotopic and anisotropic, diastereotopic stuff. So it's just like an easy way to see the definition. So homotopic, if it's the same compound, and they are chemically equivalent, if you see the trend here in the anisotropic, and then diastereotopic, and are not. Is that cool? The left side of the NMR is described as downfield, and the right side is upfield. The D-shield ones are downfield. So downshield is, yeah, left side, okay. Good? All good? So yeah, the more D-shielded I am, the higher frequency that the more energy I can absorb. Okay, 2 more pages. We're almost there. Okay, so which compound would you expect to show a M18 peak in its mass spec? M18 is indicative of an alcohol, and there's only one with an alcohol, so B. So this is that nitrogen rule. Odd number of nitrogen should have a molecular and odd number peak.
So whatever has an odd number of nitrogens, which is C. So N. That's an N rule. Okay, so how many signals would you expect to see in the H NMR spectrum of S2 bromopentane? Okay. Oh, S is going to be a dash. The reason I know that is because I just did it before. If there's, I think she remembered teaching you a rule, if there's a CH2 and there's a chirality center, those CH2 hydrogens will be not chemically equivalent. You guys remember that? So these CH2s are going to be different. Let me do these H's. So these are all equivalent. This one is not. This one and this one are different. Same with this one and this one, also different. And then this CH3, all the same. So we got 1, 2, 3, 4, 5, 6. Wait. Oh, there's also a hydrogen here. Don't forget that. 7.
Isn't it 8? 1, 2, 3, 4, 5, 6, 7.
It's okay. I feel you. No, yeah, feel free to correct me though, because that should happen. So spin splitting is basically asking which has chemically equivalent hydrogens. Okay, so they all should be basically chemically equivalent. Okay, so in this case we'd have CH3. So they're not, all the hydrogens are not chemically equivalent. These are, but this one isn't, right? Oh. Does that make sense? So all it's asking is what is all chemically equivalent. Okay? So in this case, though, for B, bless you, these hydrogens are all chemically equivalent. So the answer is B. Because this one, symmetry, both are the same. All good? Oh, sorry. Thank you. Does that change everything? 1, 2, 3. Well, I guess this one's, ooh. I did circle B though. Yeah. So I guess it's asking for symmetry. We'll come back to this. Is that okay? But the answer that it actually is B, but explanation I messed up. Okay? So we'll come back to this one. Okay? So which of the following compounds would have a base peak of 43? 43 is indicative of a what group? Or in this case, we don't have any nitrogens. So what is that? So we have an M15, we have M29, so M15 is methyl. M29, ethyl, M43, propyl, right? So we should have a propyl group coming off somewhere, right? So the one that has this propyl group is, for answer's sake, it's D. Drawing it out, if you draw it out, you'll be able to see it easier. Right now, since it's in this weird format, it's difficult for you to see. Is that good? Okay, so on to the next one. The last 3, wow. Okay, the hydrogens shown are, so when it's in a double bond, the way I look at it is if there was symmetry, then it would be enantiotopic. Like if it was, let's say, like this, with the symmetry, those hydrogens would be different, but they would still be enantiotopic. This one, double check with me though, because I do see symmetry and it could be homotopic. But I think the main thing is that these two are locked. These both hydrogens are both locked in their spots. And if I were to do a replacements test, the chirality would not change at each spot, so it would be a diastereotopic one. Sorry, very quick, not that fun explanation. And for 53, the hydrogen shown would be also diastereotopic. If I were to do a replacement test, I could see that also. Okay. So right now I'm just throwing out the answers. Okay, 50. What time is it? All right, we got 2 minutes. We're blowing through this one, and then we'll see if I have time. I'm gonna go ask. Okay, so a compound shows IR, so I guess I don't have to do HDI. So usually the first thing you do is HDI to check. In this case, if I wanted to quickly go through this and I was running out of time, I look at how many signals I have. So in my H1 NMR, and it says none, so let's look at my IR first. So no signals from 3300 to 3400, so that means no alcohols or carboxylic acids, right? So any alcohol, carboxylic, okay, sweet. So C's out. So let's see how many signals I get in my H1 NMR. And I only have 2 signals, so I should only have 2 non-chemically equivalent hydrogens, right? So in this case, I have just one. So just one set of chemically equivalent hydrogens, so only one signal should show up in my H1 NMR. Actually, wait, and then I have these hydrogens. So I should have 2 signals. So this could be it. This one's already out. This one only has, this one only has 1 signal, so this one's out, right? Because all these hydrogens are the same. There should be 2 hydrogens on each one. But now it's between, let's just check. So we got these hydrogens are the same, and these hydrogens are also the same. So we got 2 signals. So now let's look at our C13 NMR. We're looking for 3 not chemically equivalent carbons. Okay? So in this case, this has 1, 2, 3, 4, too many. Okay? So too many chemically equivalent. I can't say chemically equivalent. Okay? So in this one, this has 1, 2, 3 chemically. All right, so that matches up with my signals. So A. That makes sense? We all good? Cool. Thanks for coming, guys. Sorry for the rushed ending where explanations were thrown out the window. I think I'm going to try and post the last few pages at least, answers-wise, and put a little bit more explanation on the ones that we rushed through. So check the WordPress site either today or tomorrow. Okay? And once again, thank you for coming. Take care.